Hello everyone. In this lab we will try to create a custom IP. In the previous lab you have an additional Verilog module. You added it in your block design, but it was not a custom IP. It was just we added that module over there, right? Both were in the same project also. Now we will create a custom IP so that this IP can be reused in any other projects and by any other person, right? I will just explain you my complete intention. So I will create a hardware that can do image inversion. That is my target. So we'll start with a particular IP that can perform that task. Then later we will create a block design in which we will use this customized IP, and where we'll write the VTIS code to feed some input and check whether it is getting negative, we are getting the negative or not. So I'm just creating a new project. So this is my image negative, or let me type IM negative. So I'm selecting my board, ZCU102, finish. So as I said earlier, here I will have two projects. One project is for creating the custom IP, and second project is the block design in which I will be using this IP. Okay, so if you look at the folder structure directories, so this is my project folder. Right now you have the project related to IM negative module. Okay, so I'm creating a module called IM negative. I will write the source code for that. So let's give a name IM negative. Okay, so this is your Verilog code. I have already a code with me. We'll explain it. So module IM negative. So this IM negative is actually an IP block which has to communicate data with the PS. So here we are incorporating the DMA controller into the role. So the DMA controller is required here to transfer data between the PS and the IP that you are designing. So this is your device. We will call it a device because that's the terminology used by Vivado. So we have to transfer data from the PS to the device. So device is actually the module who is performing. This is your hardware who is performing the inversion. So he will take the negative of your image. Now talking about the DMA controller, so this module has to be designed so that it has to communicate with the DMA controller. So the protocol used for communicating with the DMA control is not AXI, but it is AXI stream. Okay, we will be using AXI stream. Let us see what are the inputs to this module. So in order to make it more generalized, instead of directly using the data width as 32 or 8, whatever it is, we have defined it as a parameter like this. So you have to use this hash symbol with parameter data width is 32, or you can neglect all these things, delete this and delete this thing. You can simply write here 32 or 8 accordingly. Okay, so it's much more easy structure. Now you have the AXI clock and AXI reset. These are the inputs. If you look at the other part, here the ideology is that the DMA has to communicate with this module. So that is through the AXI stream protocol. Okay, so the AXI stream protocol, we have to apply it in two ways here. So you have a slave interface and you have a master interface. So what is slave interface? So slave interface is the section where that receives the data from the DMA. Okay, so the DMA will be sending the data and this will be the input for me. It will be an input for me. And there is a handshaking mechanism over there. So there are two signals associated with that, that is valid signal and ready signal. It's simply valid and ready. So here this is the structure that Vivado used for the nomenclature. S for, we are also following the same thing. S for slave. Okay, and this is the protocol. What is your protocol? It is not AXI, it is AXI S, AXI stream. That's why it is access. Okay, So you are using AXI stream protocol to communicate between DMA and the module or your device. So this is the slave interface. So this is the part who is receiving the data from the DMA controller. Where DMA controller will get the data from the PS. PS will give data to DMA controller and he will give it to the module. So this module has a two inputs, which is one is data obviously, and another thing, data will be named like this as access data. And when he will receive the data, whenever he is ready, he will receive the data. So this ready is the signal that will inform the DMA that I am ready. So it's the output signal from this section. So this is the output signal. Now when the DMA receives this signal, and if DMA is having a valid data, okay, when he is ready, that doesn't mean that he will get the data immediately. There should be valid data to be sent from the DMA. So the DMA will inform this device that I have a valid data using this signal, that is S-axis valid. So whenever X-axis valid is high, that means there is a valid data to be sent from the master. The master is the DMA, so he will receive it. That will be the coding section. We will see that. And now let us focus on the master interface of your device. Device means this negative image negative module. So the device master interface has to send the processed data. After taking the image negative, he has to send it back to the DMA. Okay, so obviously this data will be M-axis data, M for master, axis stream data. This will be actually output from your device, because the device is sending the process data. Now when the processing is complete, he will have a valid signal. He should give a valid signal to the DMA. He should inform the DMA that I have a valid signal. So that's why I have another output line called M-axis valid. Now what is M-axis ready? So this is input to my module. So this is actually the ready signal that is sent from the DMA. So you cannot send always data. You can send only when your DMA is ready. Okay, so you have to check this thing. When your M-axis is ready, then only you should, when you have a valid data, then you send it. Okay, so that's what is programmed here. So here you can see that your slave is ready when your master is ready, because when you are getting ready, when the DMA is ready, you are getting ready. Okay, that's what you're doing there. And if you look at the always block, you can see that always at pause edge of axis clock, what's happening over there. So you are processing the data. These are the lines to process the data. You are processing the data only if you have a valid signal. That means you have a data and you are ready. Okay, so when you are ready and you have a valid data, you are just processing the your particular role. And in my case, my role is to take the negative. So taking the negative is done like this: 255 minus. So you know that maximum it's 255. So you can deal with only 8-bit data. So it is, if you have the data with us 8, it's simply directly 255 minus S-axis data. So what is X-axis data? That is the input you are receiving. Okay, X-axis data is the input that you are receiving from the DMA controller. You have to take the negative, that is 255 minus S-axis data. You can just focus on the selected line, and you have to assign it to M-axis data. What is M-axis data? That is the output going from your device to the DMA. So M-axis data is the output and X-axis data is the input. You can conclude like that. So you have the input, you take the negative, you assign it to your output. And this for loop will ensure that if you are trying, for example, in this case, I have 32-bit data width. So you have say 8 into 4 is 32, right? So you have to run this for loop 4 times. So this is 32 by 8. It will be 4, I less than 4. So 0 to 3 it will work. So when I equal to 0, what will happen? This is I into 0 into 8. So this is 0. So starting from 0, you have 8 bits. That's the meaning of this. So it's like 7 to 0. Okay, instead of writing for the first iteration, it will be like this: 7 is to 0. Instead of writing that, you can use this programming style. So this is like this. Once again, 0 is the first position. Then you have 8 bits from that. So it's like 0 to 7, or usually we like 7 to 0. Okay, 7 is to 0. And in the next loop it will be what? Data I will be 1, so this will be 1 into 8. So from starting from 8 to the next 8 bits. Okay, so that will be again 0 to 7 has been done in the previous iteration. So next will be from 8 to 15. Okay, or you write 15 colon 8. So that's it. So with four loops for this example, since it is data width is 32, all inversion or negative will be done. Okay. So here your x-axis valid is assigned as m-axis valid, because s-axis valid is my valid signal you receive from the DMA. Once you have done this, you will assign it back. So now let us see. Let's save this code. Now I'm not directly going into the block design. Instead of that, I'm going to package this as a IP. So in order to do that, you have to go to Tool, Create and Package New IP. Create and Package New IP. Click Next. So package your current project. Here you can see Create AXI for peripheral. There is an option like this, but I'm not dealing with AXI peripheral. I'm creating AXI stream peripheral. So you go with the same thing. Package your current product. This is safe in all the cases. And do remember one thing. This is the repository where you are going to save your custom IP. Do not disturb the root folder of your Vivado. Always it is recommended to create a folder to save all your IPs. Okay, so I have a folder like this, my IP. So in which I will be storing all the IPs, and in order to distinguish it, I am going to create as a IM negative, another folder here, IM neg, okay, or negative. So in this folder, I will be saving this particular IP. Okay. So you select that particular folder instead of your Xilinx folder. You go to your particular folder, especially this thing. Okay, because we will be having more IPs in the coming labs. So in order to distinguish the projects, it's better to save like that. So this is the repository in which I will be saving my IP. Okay. So just ensure that you have any space or anything, nothing. Okay. So the message that I got here is that the project source file will be copied to the indicated IP location directory. So to this directory, our current project will be copied, complete all source file will be copied as a temporary project. And further, when you want to edit your IP package, you have to work on that particular project only, not on the current project we are working on. I will show you that. So once it is finished, you can see that Vivado is opening another project. So you can see the heading temporary edit project.xpr. So if you look at the Vivado tab, here you can see IM negative. This is the project I started with. Now Vivado has copied this project to another project called temporary. So Vivado will all the packaging related things you do over here. Whenever you want to repackage, once after packaging you want to modify your package, you have to work on this temporary project only. Okay, we'll see that. So you should get all these sections verified. So here you can see that the first thing is identification, compatibility, file groups. So identification, here you can give negative, you can give name to your module. So this is IM underscore negative. You can give your custom module. You can create your vendor name. Say, can give your custom name. It should followed by .com, something like that. You can change that. Let it be Xilinx itself. And the better you can give a description also, otherwise it will end up in some warning later. Here right now you are having some warning. Okay, you are having some warning associated over there, not over identification in ports, but here in description you can give some other description. So this is the IP for, this is the IP for image inversion. Okay, image negative, IP for image negative. So get all these things checked. If you have any error, solve it. So now look at the ports and interface. You have some warning over there. We will try to troubleshoot it. So if you look at the GUI, this is the GUI for your, just maximize it. You will have some GUI here. So this is the GUI for your particular module. So you can see all inputs are in the left side and all outputs are in the right side. This is how it organizes. But when you add some IP block, you can see that it's not like that. It is usually grouped. Your slave interfaces and master interfaces are grouped. So you can do that port mapping here or grouping here. So you go to here, you can say it has already, the tool has already identified the clock here. Rest of the things you can do like this. Go to add bus interface, you select here interface definition. We are using axis stream interface. You select axis stream, axis s underscore rtl, click ok. You give some name for the master. So say the master is m underscore axis stream. Okay, using this style. So this is not slave, this is master. You can, by default it is master only. Go to port mapping. Then you have three signals here. One is valid. Okay, so which is your valid for the master? M axis valid. Map ports. Then if go to data, which is the data for the master? That is M axis data, right? M axis data. Click map port. It will be mapped here. You can see the mapping. In case if you created some error, you can remove that and you can delete it like this, unmap and map it again. And go to T ready, next signal. So which is the master ready? This one, map port, right? Parameter we will see later. Click OK. So you can see that now it is grouped. M axis it is grouped. If you look at the GUI also, you can see that it will be updated once we finish this. Now go to axis. So axis stream RTL. Okay. And now this is a slave interface. So slave axis, you can give any custom name, but it's better to keep like this. S for slave axis, and this is this S is for stream. So this is your slave interface. And go to parameter port mapping. You have ready, sorry, valid, S axis valid, slave data, S axis data, then slave ready, S axis ready, map ports. Okay. Now all those things are done. So ports and interface, it is done. Still you have some warnings here for, you can see the warnings in the messages. Let's look at the GUI. GUI has been beautifully organized, clock reset and the slave. If you expand the slave, you have the valid data and ready. Okay. Expand the master, you have the master valid data and ready. Everything is fine. But here you have some warnings. We will troubleshoot it. Let's see, look at the warnings. So the problem is regarding the clock. Okay. So the clock is not associated with it. With what? So the clock is not associated with your M axis, your master and slave interfaces. And also the frequency heads parameter is not defined for the clock. Okay. So you do one thing, go to clock. So we have to ensure, we have to give how or inform what all things has to be there associated with the clock. So first thing is, once again you can look at this, double click on axis clock, go to parameters. Here you can add the parameter. So what we need, you need this thing FREQ underscore HZ, all in capital, frequency in heads. So I have added that. You cannot see over there, it's under actually this tab, FREQ. So what is the value? So we will be operating at 100 megahertz. So 100 and 6 zeros, 1 2 3 4 5 6. Click OK. So the frequency has been assigned. Now you can see that now it's 3. Now the thing is, who will be using these clocks? So your M axis and S axis has to use that. Okay, so you have to associate the clock with them. So again, you have to add one more parameter, bus interface, that is called associated underscore bus if. Okay, associated underscore bus if. So that will be under this overridden. So here, what is the description? You just read it. List of bus interfaces, interface name separated by colons. Okay, so we have two interface, M underscore a master interface and a slave interface. M underscore axis, that was the master interface, separated by colon, not half colon, semicolon, full colon. Then slave interface, S underscore axis. Then colon is not required, you have only two. Click OK. Now we can see that all the warnings has gone. Now it's verified. GUI, everything is done. So once you have the tick mark on all this, addressing and memory is not required. All of this, when it's verified, go to review the package. Don't click package IP. Before that, just verify the edit package settings. In some versions of Vivado, if you are looking older versions of Vivado, by default this will be checked. Delete project after packaging. If it is checked, the issue is that we have the temporary project created in which all the source codes are copied, and right now we are working on that. If you click on the delete project after packaging, that temporary project files will be deleted. You cannot edit your package anymore. Okay, so definitely we may face some issues and we have to edit our package later. So it's always safe to uncheck this. Okay, delete project after packaging, uncheck that. So that's all. Now apply that. Okay, now you can package your IP. So Vivado is asking to close the temporary project. Let me click no, because I want to show you one more thing. Somehow if you have closed this thing, you can open it again from this. So if you look at the design source, you have one folder here, component.xml. This is the file actually will open this. Now it's not opening, you have to close the project again, and if you open this temporary project again, you can open that packaging thing. So where I will find it, that is in your my IPs, IM negative, you have the temporary edit project. So if you open this project, you can edit your, we have already packaged the IP, but later if you want to edit, you can edit it. And you cannot see the component editing things over there. So you can double click over there, it will open up and you can modify anything if you require. So right now I'm closing my project. So we have packaged the IP. Your IP will be available in this repository, right?